In this video, I'm going to introduce the summation notation in mathematics. First of all, let's see why we need the summation notation. Take a look at this example. Suppose I want to represent that S is equal to the sum of the numbers 1, 2, 3, 4, 5 all the way to 21. Of course, it will be too lengthy if we write down all the 21 numbers in this expression. We can actually use ... like this to write down this expression more concisely. However, this ... representation may sometimes be problematic, because this ... requires the readers to interpret the number pattern on their own, and different people may have different interpretations. For example, after 1, 2, and 3, it may not be 4, if the reader is having the Fibonacci sequence in mind. In other words, this ... sign leaves ambiguity in the expression, and this ambiguity is definitely undesirable in mathematics. So the summation notation was invented to represent this kind of expressions more precisely. In this example, this expression can be represented by this summation notation. This symbol is called the summation sign. This is a Greek letter read as sigma. Then this I is known as the index of summation. And this 1 and 21 are the lower limit and the upper limit of the summation respectively. And then inside this summation sign, this expression refers to each term in the sum. This is usually known as the general term of the number sequence. We can understand the summation notation as a representation of a table like this. In the summation notation, we only need to specify the first index and the last index. And then the readers will know that there is a list of indices like this. For each index, the corresponding term can be known by referring to the general term stated here. Then, the value of the summation is just the sum of all these terms. Now, let's change the situation a little bit. Suppose now the sum that I'm interested in is 2 plus 4 plus 6 plus ... plus 22. That means the sum is a list of even numbers. In this case, the table would be like this. The indices are still 1, 2, 3, 4, 5, so on and so forth. But now the terms are 2, 4, 6, 8 all the way to 22. In terms of the index I, now the general term should be 2i. So that when I is 1, the term is 2. When I is 2, the term is 4, so on and so forth. From this pattern, we can see that the last index of the summation should be 11. Because when 2i is equal to the last term 22, I is equal to 11. Now let's take a look at this situation. Suppose we want to express 4 plus 6 plus 8 plus ... plus 22 in the summation notation. In this case, the table is like this. The indices can still be 1, 2, 3, 4, 5, so on and so forth, and the terms are 4, 6, 8, 10 all the way to 22. In terms of the index I, now the general term is 2 times I plus 1. And the last index will then be 10. In fact, the index is not necessarily to start from 1. In this case, if the index starts from 2, then the general term can be simpler like this. On the other hand, the index is also not necessarily to be denoted by I. We can choose other letters to denote the index. For example, it can be R and it can be K. As we can see, no matter what letter we choose to denote the index, the expression represented by this summation notation remains exactly the same. So in mathematics, we call this variable a dummy variable, meaning that it is not really a variable, and the result of this summation will not be in terms of this variable. Now let's take a look at a few examples to apply the knowledge of the summation notation. In the first example, the values of T1, T2, T3, and T4 are given. Now we need to find the value of this summation. By definition, this summation expression can be expanded as these 4 terms. By direct substitutions, we can get that this summation is equal to 68. Next, let's take a look at this example. Here we need to evaluate this summation. Again, by definition, this summation expression can be expanded as these 5 terms. Hence, this summation is equal to 270. Next, in this example, we need to rewrite this expression in summation notation. First of all, we need to find the general term of this number sequence. Since the index of summation may not start from 1, there can be many possible ways to express the general term. One way is to consider the general term to be 4 plus 3i. For this general term, when it is equal to 4, I is equal to 0. That means the index should start from 0. And then when the general term is equal to 19, I is equal to 5. Hence, the summation notation is expressed in this way. The general term is 4 plus 3i, and the index is from 0 to 5. Afterwards, let's take a look at this example. This example shows us how to change the lower limit of summation. The original index starts from 3, and now we need to change it to start from 1. To make this change, we need to change the general term. Firstly, we can consider a new index I, which is equal to r minus 2. In this way, if r starts from 3, I should start from 1. And if r ends at 8, I should end at 6. Therefore, the summation can be rewritten in this way. The new index is I, and it starts from 1 and ends at 6. And then we substitute I plus 2 into r. So this is the new general term in terms of the new index I. After simplification, the required expression is then equal to the summation of I plus 2 times 2i plus 3. If we still want to use this r to denote the index, we can further rewrite this expression like this in terms of r, because the index is just a dummy variable, so it can be denoted by any letter. Before we come to the last example in this video, I would like to introduce some useful properties of the summation notation. In the following expressions, we assume p and q are constants, which means they are independent of the index. First of all, we should know that in summation, constants can be taken out. To understand this, we can take a look at this example. For the summation of 7ti, 7 is a common factor of these terms. Therefore, it can be taken out like this. In other words, this property simply means that we can take out a common factor in the summation. Secondly, we should know that the summation notation can be expanded like this. Summation of x plus y is equal to summation of x plus summation of y. To understand this, we can take a look at this example. For the summation of x plus y, we can rearrange and regroup the terms like this. In other words, this property simply means that we can regroup the terms in the summation. The same property goes for x minus y like this. Summation of x minus y is equal to summation of x minus summation of y. We can compact these three properties in a single formula like this. On the other hand, we should also know how to calculate the summation of a constant. We have a formula like this. The summation of a constant p is equal to b minus a plus 1 times p, where a is the lower limit and b is the upper limit. To understand this, we can take a look at this example. For this summation of 3 from 2 to 6, no matter what the index is, because this 3 is a constant term, so all the terms are the same like this. And there are 5 such terms from index 2 to index 6. So it is equal to 5 times 3. To calculate this number 5 from the lower limit 2 and the upper limit 6, we consider 6 minus 2 plus 1. That means the upper limit minus the lower limit plus 1. This is how we can count the number of integers starting from a and ends at b. Finally, let's take a look at this example. Here we need to evaluate this summation. Instead of evaluating this by direct expansion like previous examples, this time we can try to apply properties of summation like this. In this way, we just need to evaluate this simpler summation and this constant summation. As a result, it is equal to 230. This is how we can understand and manipulate expressions involving the summation notation.